Okay, I will. So welcome everyone for the penultimate lecture. We have the last lecture is tomorrow, and so I will first of all introduce Professor Watanabe to all of you. That we actually Professor Watanabe graduated from our university in Niigata, and he is actually specialized in volcanic rocks in his doctoral course, but later on he moved to hazard research, and so he is now actually concentrating on different sort of how I should say put it up as a hydrologic cycle that and also looking at hot springs, looking at movement of water related rainfall related landslides and earthquake related landslides, and those kind of hazard research, hazard related topics he's concentrating on. So I suppose he's going to give a general overview of his introductory part of how to look at the as you know, Japan is very prone to these kind of hazards, so you may get a very general outline of what is going on here in Japan, I think. Thank you very much for agreeing for give a lecture on this topic, and I look forward to your lecture. Thank you. Please.
Okay. Okay, thank you, Chairman, Professor Satish-san. I'm very happy to get opportunity to give my talk. So now I would like to begin my lecture. I'm Naoki Watanabe at Niigata University, and my research interest is the mechanism of the slope disasters. So I am investigating the relationship between groundwater behavior and landslide occurrence using some approaches from hydrogeology, engineering geology, and hydrogeochemistry. I will go through these contents on today's lecture. These are all very basic contents. First, sorry. I will talk about basic information of landslide. Second, I will talk about the factor of landslide occurrence. And next, I will talk about climatic and geologic condition in Japan as the background of landslide occurrence. And finally, I will introduce some example of landslide, focusing on the triggering of landslide. First, I will explain some basic information. This chapter draws on the literature presented here. This handbook is available to download from the USGS website here. I recommend this book if you want to advance your study of landslide. So, What is a landslide? A landslide is defined as the movement of mass of rock, debris, earth, or soil down the slope. Landslides are a type of mass wasting which denotes any downslope movement of soil and rock under the direct influence of gravity. The term of landslide encompasses mainly 5 modules of slope movement. First, falls, second, topples, third, slide, fourth, spread, and fifth, flows. This further subdivided by the type of geologic material, for example, bedrock, debris, or earth. Debris flows, commonly referred to as mud flows or mudslide, and rock falls are example of common landslide type. Excuse me, I would like to turn off my video because my PC is quite old. So for the performance of presentation, so I turn off video. Sorry. Okay, generally, landslide can be classified into different types based on the types of landslide movement and the of landslide materials. In brief, material in the landslide mass is either rock or soil or both materials. The latter is described as earth if mainly composed of sandslide or finer particles, and also described as debris if composed of coarser fragments. The type of movement describes the actual internal mechanism of how the landslide mass is displaced. That is, fall, topple, slide, spread, or flow. Now, let me explain the phenomena of cold fall. As shown in figure and picture, the most common phenomenon is rockfall. Falls abrupt downward movement of rock or earth or both that detach from steep slope or cliff. The falling material usually strikes the lower slope at angle less than the angle of fall, causing bouncing. The falling mass may break on impact, may begin rolling on steeper slope, and may continue until the terrain flattens. Next, explain the topper. The topper, like this, is recognized as the forward rotation out of a slope of a mass of soil or rock around the point or axis below the center of gravity of the displaced mass. Toppling is sometimes driven by gravity exerted by the weight of material upslope from the displaced mass. Sometimes toppling is due to water or ice in cracks in the mass. Tops can consist of rock, debris, or earth materials like soils. Next, let's take a look at the slide. The landslide on which the surface of rupture is curved upward like spoon-shaped, and the slide movement is more or less rotational about an axis that is parallel to the contour of the slope like this. The depressed mass may move as a relatively coherent mass along the rupture surface with little internal deformation. The head of the displaced material may move almost vertically downward, and the upper surface of the displaced material may tilt backward toward the scalp. This is the name of various parts of the landslide body based on Barnes 1978. This figure is very famous, and for example, crown, main scalp, head, toe, foot, main body, right flank, and so on, something like that. Next is a translational landslide. The mass in a translational landslide moves out or down and outwards along the relatively planar surface with little rotational movement or backward tilting. This type of slide may progress over considerable distance if the surface of rupture is sufficiently inclined, in contrast to rotational slide, which tend to restore the slide equilibrium. The material in the slide may range from loose in unconsolidated soil to extensive slabs or rock or both. Now, translational slides commonly fail along faults, joints, bedding surface, or the contact between rock and soil. Next, I will explain spread. Lateral spreads are usually like this figure, usually occur on very gentle slopes or essentially flat terrain, especially where a strong upper layer of rock or soil undergoes extension and moves above the underlying softer, weaker layer. In rock spread, solid ground extends and fractures, pulling away slowly from stable ground and moving over the weaker layer without forming a surface rupture. The softer, weaker unit may squeeze underward into fracture that divides the extending layer into blocks. In earth spread, the upper stable layer extends along the weaker underlying unit that has flowed following liquefaction or plastic deformation. I'll talk about several flows. A form of rapid mass movement in which loose soil, rock, and sometimes organic matter combine with water to form a slurry that follows downslope. Occasionally, as a rotational or translational slide gains velocity and internal mass lose cohesion or gains water, it may change to a debris flow. Dry flows can sometimes occur in cohesionless sand, and the debris flows can be deadly as they can be extremely rapid and may occur without any warning. Next one is lahar. And the word of lahar is an Indonesian term. Lahars are also known as volcanic mud flows. These are flows that originate on the slope of volcanoes and types of debris flow. The lahar mobilizes the loose accumulation of tephra and related debris. Debris avalanches are essentially large, extremely rapid, often open slope flows formed when an unstable slope collapse and resulting fragmented debris is rapidly transported away from the slope. In some cases, snow and ice will contribute to the movement if sufficient water is present, and the flow may become a debris flow or lahar sometimes. Earth flows like these figure and picture, earth flows can occur on gentle to moderate slope. Generally, in fine-grained soil, commonly clay or silt, but also to very weathered clay-bearing bedrock. The mass in earth floor moves as a plastic or viscous flow with strong internal deformation. Susceptible marine clay, as you know, quick clay, when disturbed, is very weak and may lose all shear strength with a change in its natural moisture content. Such clay suddenly liquefy, potentially destroying large areas and flowing several kilometers. Creep is a very, very slow earth flow and steady downward movement of slope forming soil or rock. Movement is caused by internal shear stress sufficient to cause deformation, but insufficient to cause failure. Generally, the three types of creeps are first is seasonal, where movement is within the depths of soil affected by seasonal changes in soil moisture and temperature. Second one is continuous, where shear stress continuously exceeds the strength of the material. And third, progressive, where slopes are reaching the point of failure for other types of mass movement. Okay, the second chapter is a factor of landslide. Here I talk about the cause of landslide occurrences. Of course, almost landslide have multiple causes. Commonly, slope movement occurs when forces acting downslope, mainly due to gravity, this one, exceed the strength of the earth material on the slope. Causes include factors that increase the effect of downslope force and factors that contribute to low or reduce strength. For example, these figures show an influence of groundwater behavior. When the groundwater table or pore water pressure in the slope rising up, the strength of material near the sliding surface is decreased. As a result, sometimes landslide occur. Here is the three major factors of landslide. One is the geological causes, second is geomorphological causes, and third one is human causes. The first factor is related to geology. First, weak or sensitive materials. Second, weathered materials. Third, shared, jointed, or fissured materials. Fourth, adversely oriented discontinuity, such as bedding, cystosity, fault, unconformity, contact, and etc. Fifth is contrast in permeability and stiffness of materials. Next factor is related to morphology, including hydrogeological condition. One, tectonic or volcanic uplift. Two, glacial rebound. Three, fluvial wave or glacial erosion of slope toe or lateral margins. Four, subterranean erosion, solution, and piping. Five, deposition loading slopes or its crest. And six, vegetation removal by fire or drought. Seven, thawing. Eight, freeze and thaw weathering. And nine, shrink and swell weathering, and etc. The final one is related to human activity. One, it's a difficult pronunciation. Excavation of slope or its top, loading of slope or its crest, drawdown of reservoirs, deforestation, irrigation, and six is mining, and seven, artificial vibration, and eight, water leakage from utilities. There are another category of factors of landslide. Internal factors are related to the soil and rock materials in slope. First, soft and weak rock properties due to various weathering. Second, rock strata with multiple joint or shear fracture zone. Third, geological structure, bedding, cystosity, fault, and so on. Fourth, topography, such like slope angle or shapes of slope or valley, and catchment system. And fifth, vegetation, and so forth. Internal factors nearly equal susceptibility of slope. Contrasted with internal factors are external or triggering factors. Landslide can be initiated in slope already on the verge of movement by the following triggering factors. One, heavy rainfall. Two, rapid snow melt. Three, change in water level. Four, stream erosion. Five, changes in groundwater. Six, earthquakes. Seven, volcanic activity, 8, disturbance by human activity, or any combination of these factors. Okay, in chapter 3, we will overview the climatic and geological condition in Japan. This provide the background for landslide in Japan. There are roughly 3 climate zones in Japan. The northern part is frigid zone, and southern part is subtropical zone. As you can see, most of Japan is the temperate zone. And Japanese climatic condition is also classified into 6 categories. Those are Hokkaido type, Pacific Ocean side climate, and Sea of Japan side, inland, and Seto Island Sea type climate, and Nansei Islands type climate. This figure shows annual precipitation and temperature variation for cities representing each climate zone. These figures summarize the climatic characteristics of each climate zone. The climate condition in the Sea of Japan side tend to have more precipitation in winter season, like this. And Hokkaido and set inland sea areas are characterized by low annual precipitation. This figure shows average annual precipitation during 1971 to 2000. The annual precipitation of Japanese islands shows ranging from less than 1,000 millimeter to more than 3,000 millimeters. A very wide range. This figure shows snow depths in winter season in Japan. And heavy snowfall occurs mainly along the Sea of Japan side. I will briefly explain here how mechanism of snowfall along the Sea of Japan side. There is a high pressure, high atmospheric pressure system on the continent and a low pressure system in the Pacific Ocean. And so cold and dry wind from Siberia blow from northwest to southeast directions. When this cold and dry winds pass over the Sea of Japan, the wind pick up large amount of water vapor because warm current, Tsushima Kairyu, warm current flows along the Sea of Japan side. Such vapor generates large amount of snow cloud and causes of heavy snowfall. This is a schematic model for the mechanism of heavy snowfall. Cold and dry air mass from the Siberia pass over the warm sea and become high humidity air mass, and then rising up along the mountain slopes and is cold according to temperature loss rate. Consequently, a large amount of snow clouds are generated. These photos show the record-breaking heavy snowfall in middle to southwest area of Niigata Prefecture in January 1963. Okay, moving on to the topic of geology in Japan, but however, we don't have enough time for detailed explanation. Maybe other professors talked about or will talk about geology in Japan. So I sorry, I neglect detailed explanation. Therefore, I will focus on the topics related to landslide. This figure shows the distribution of landslide superimposed on the geological map of Japan. It's difficult to identify. And according to a simplified figure, the bedrock geology of landslide in Japan can be divided into three main categories. Pinky area shows fault fracture zone, this one, around here. And blue area shows neogen sedimentary rocks. And orange area shows hydrothermal alteration zone along near the active volcanoes. Here we will focus on two areas around here and around here. Two areas of high landslide density. One is the area in Shikoku surrounded by the red line, which is an area of fracture zone. The other is the area surrounding by blue line, which is an area of Neogene sedimentary rocks. The distribution of landslide in Shikoku Island shows that the landslides are concentrated in the area of Sambagawa metamorphic rocks. This color is pinky color is Sambagawa, shows Sambagawa metamorphic rocks. And between the median tectonic line and Mikado tectonic line, like this. As you can see, the Sambagawa metamorphic rocks are composed of various types of crystalline cysts. As you know, the cysts have well-developed cystosity and joint and fractures caused by faulting and weathering also observed. These structures are good candidate for sliding surface or separation plane. Let's go back the characteristic of climate condition. The Seto Island Sea, northern part of Shikoku Island, was characterized by low annual precipitation. So, what triggers landslide? The answer is mainly typhoons. It varies from year to year, but in 2004, 10 typhoons passed through Japan, especially Shikoku Island around here is an area with a high probability of typhoons passing through. Both photos show the Azue landslide caused by a typhoon in 2004. Yeah, I will explain landslide on Neogene sedimentary rocks. This map shows the distribution of landslide on the geologic map of Niigata Prefecture. And this is the area enclosed by the blue line in the previous slide I mentioned. As you can see, landslides are concentrated. Landslides concentrated in the yellow-colored area. That is in the area of Neogene sedimentary rocks. Now I will introduce the Neogene sedimentary rocks. These rocks are called sedimentary soft rocks because these rocks can easily be pierced by the hammer pick. And these are easily weathered fine-grained and softened. Left side photo shows outcrop of weathered siltstone with slaking. And right side photos showing a kind of slaking test, exposing fresh siltstone under the open air condition. It was only 2 days, 75 days later, it was rapidly weathered and fragmented. And I will explain some example of landslide on the Neogene sedimentary rocks later in relation to several triggering factors. I'll talk about landslide in hydrothermal alteration zone near active volcanoes. Both photos show the Hijiori landslide in the Hijiori caldera, Tohoku region in Japan. Bedrock, in general, bedrock has been altered into clay minerals by humaroric and hydrothermal activity near the volcano. And then the shear strength of bedrock is significantly reduced due to the hydrothermal alteration processes. Both photos show the Sumikawa landslide occurred May in 1997. The area enclosed by red line shows whitey area, shows thin layer of ashfall associated with this landslide. The unloading of the overburden pressure by the landslide movement caused a small steam eruption. So ash flow fell in around here. These three photos shows landslide prevention works in humaroric areas of the Hakone volcano. It's one of the famous resort and volcano in Japan. Okay, chapter 4 is on the topic of natural triggering factors of landslide. In this chapter, I will talk about landslide with different triggering factor on Neogene sedimentary rocks. The first is snow melt induced landslide. As you know, several landslide occurrences are caused by increase of poor water pressure between a slippery layer of clay and the underlying bedrock due to infiltration of rain or snowmelt water. Landslide in the Sea of Japan side region, its snowy area, often occur during the spring season, which is caused by rising up the groundwater table or poor water pressure due to the snow melting processes. When water added to the soil mass, the shear strength increased because of the increase in total weight. On the other hand, high pressure of poor water decreases the normal stress affecting on the sliding surface, and then also decreases the shear resistance of the soil mass. We return to this map. Please remember some areas of high landslide density zone, yellow colored area. This figure shows an example of snow depths in Niigata prefecture on 12th February 2012. This is our institute downloaded from our institute. As you can see, the landslide area overlapped the snowy areas. So I will now show you several photos of snowmelt-induced landslide. This is a Tamanoki landslide occurred in February 1985. This is the Kamihiramaru landslide occurred in April 910. This is the Kokugawa landslide occurred in March 212. Both photos are the Tanne-Hirota landslide occurred in April 2015. The next topic is heavy rain-induced landslide. Heavy rain fell in the landslide area on neogen sediment rocks in Niigata prefecture. This outline of the disaster. On July 13th, 2004, record-breaking rainfall occurred in the middle part of Niigata prefecture. Daily precipitation on July 13 was 421 millimeters in the Tochio area. A lot of slope failures, landslide, and debris flow occurred in mountainous and hilly areas. Unfortunately, 15 people were killed. 30 houses were completely destroyed, and 128 houses were partially destroyed, and 7,000 houses flooded above floor. The total number of various landslides was 2,215. I will show you several photos of some kind of heavy rainfall induced landslide. These are slope failures. This landslide occurred on 13th July 2004. This debris flows. Okay, moving on to the topic of earthquake-induced landslide. The Mid-Niigata Prefecture earthquake, so-called the Chuetsu earthquake, occurred near the well-known landslide-prone area. Date is around 6 p.m., October 23rd, 2004. Magnitude of JMS scale was 6.8. Depth of hypocenter, not epicenter, is 13 kilometer in depth. And the seismic intensity of GMS scale is 7. The 7 is the uppermost scale of seismic intensity. And total sediment volume was 100 million cubic meters. And landslide with sediment volume more than 1 million were 10. And the number of landslide dam were more than 50. This slide shows a failure test of model slope with several kinds of sensor by using a vibration test machine. And the test was conducted by applying artificial seismic motion equivalent to a seismic intensity of 6 on the JMS scale. As a result, seismic acceleration was amplified from the bottom to the top of slope. The maximum acceleration occurred at the corner of the slope, where the top of the slope transit to the flat surface. Just prior to the failure, the seismic acceleration was approximately twice of given acceleration to the slope. So I will also show you several photos of some kind of earthquake-induced landslide. This photo shows many slope failures. These are also slope failures. These are also slope failures. This photo shows the Shiotani Kamisama-gawa landslide. This landslide was the biggest landslide induced Chuet's earthquake. And the length of landslide is approximately 1 kilometers, and the width of landslide also 1 kilometers. This is the Higashi Takezawa landslide. This is a main scarp of the Higashi Takezawa landslide. Move to this direction. And this landslide dammed the Imo River. This photo also shows the Higashi Takezawa landslide taken from opposite side. This is the Herano landslide. This landslide also dammed the Imo River. Okay. In closing remarks, Japanese hilly and mountainous area account for about 75% of the total area. Weak geological materials are widely distributed. And in addition, annual precipitation over large areas exceeds 2,000 millimeters. Occasionally, earthquake and volcanic activity also occurred. Therefore, Japan is a high-risk country for landslide. Approaches from geoscience can make a significant contribution to disaster mitigation, I believe. Thank you so much for your attention.
Okay. Thank you, Watanabe-san, for a very informative lecture. And perhaps someone likes to ask some question, they can put it in the either, or they can come up and ask their question, or using the chat, they can ask the questions. Is there anyone who would like to ask questions? Okay, there is one in the chat. What do the landslide prevention works involve? It's from Hughes from, I suppose he's from Macquarie or from Australia. So Watanabe-san, can you say something about landslide prevention work?
Okay. under the Japanese climate condition, removal of groundwater is very important. So at the beginning, most of landslide, in most of landslide, we installed groundwater drainage system. And next one is hard countermeasures, pile and rock bolt or anchor, something like that. In Japan, first priority is removal of drainage of groundwater. Right?
Yeah.
Okay.
Is it okay, Charles? Does the groundwater drainage cause ecological issue and is it controversial? Okay, so ecological issues, yeah.
Yes, it's a difficult problem, but first priority is human, what to say,
safety.
safety. Yes, yes. And the second one is ecological issue. Recently, our government pays attention to the ecological issue for disaster prevention. Actually, day by day, gradually increase for ecological or environmental issue countermeasures. Sorry, difficult question.
Okay. Oh, is it okay? Thank you. So another question from Krishnaveni. Do you have any comments on global warming effect on landslides in Japan? Okay, that's a good question. Yeah, global warming. How about rainfall?
Okay. Yes. By the global warming, rainfall will become strongly and frequently. So I'm not sure in the future, but I suppose certainly landslide increase under the global warming condition in Japan. Actually, typhoon or heavy rainfall is, I feel, increase of frequency of heavy rainfall now, right?
Yeah.
Okay.
Sorry,
Sorry, my poor English.
that is exactly what I also think it is. So what to say? You get although the total rainfall is same, but very heavy rainfall in a very short time. That is one of the main reason for landslide, I suppose. Is it not? Yeah. Okay, so any other questions? How to manage landslide disaster caused by rainfall in lateritic zones like in Africa. Okay, so that's a question about tropical regions, perhaps.
Sorry, I cannot answer in short time because I need some time for consideration for this question. What to say?
Yeah, I
Yes,
understand because
yes,
it is
yes.
different topic of because in Japan we do not have lateritic zones, so we have I suppose in Japan we do not have that much experience of dealing with laterite zones. So that's the reason, is it not, Watanabe-san?
And maybe probably lateritic zone. How is vegetation in lateritic zone? I suppose the poor vegetation zone.
Yes.
So maybe landslide will occur caused by rainfall. But it's very difficult. Annual precipitation depend on vegetation, so it's very difficult to supply water. Probably, I think it's effective to protect surface erosion, but I don't know how to protect now. So if you give me time, so I will consider consider any idea for landslide. Sorry.
So I think Abdullah Ahmad is a student of mine, so he's here in Niigata, so he can come to you and discuss later. Okay, he's from Africa, that's why he asked about his own. Yeah, okay, I will ask him to go to you and discuss with you.
Okay. I prepared the format for question form. Now I prepared. I provide the Word file through the chat system.
Okay, okay, that's great.
Zoom.
Yeah, so you can write and or later on you can contact the student to answer with an answer. Yeah, that will be best.
Yes. Yeah. And which is attachment?
Oh, it's an attachment. Okay. So those who like to ask questions, you can download. Watanabe-san will be uploading a Word file in the chat, so you can download that Word file, and so we can close the share screening. Watanabe-san, everyone is seeing that. So.
Okay, now I'm sending
yes,
question forms.
Yes, I can.
So yes.
So please, those who like to ask questions, please download, and maybe you can send it to Adira so that she will collect it and communicate with Watanabe-san so that you'll not get disturbed too much. Okay.
Okay. If possible, you will send attached file by coming Saturday.
Yeah, that will be.
Yes, I hope.
Yeah.